Okay, so here is a short recap. We look at the Poisson process as an idealization of a stochastic process for a molecular motor like kinesin walking along microtubules. It's defined by a single object, the forward hopping rate. And then what we just did is we calculated the waiting time distribution using divide and conquer, deriving a differential equation, and then arriving at an exponential distribution of the survival time. And I forgot to mention that the waiting time distribution, so not the cumulative distribution, but the waiting time distribution, is, as usual, the derivative of the cumulative distribution function. That's given by this expression, which is basically the same as this one, just has a factor nu in front. So now that we have this waiting time distribution, we can do something super important. We can design a simulation algorithm for a stochastic process. And the simulation algorithm that I show you is really the simulation algorithm for stochastic processes. It's used universally for all stochastic processes, and it's an exact representation of the stochastic process. So it's not a Monte Carlo simulation that approximates a partition sum. It's really an exact simulation method. Now let us ask how you would simulate that. So for that, I use slides, because I want you to focus on the ideas. So let's first think about how you would simulate that, right? We could say that we go back in our reasoning to a fixed time step. So discretize time in units of delta t and use that in order to simulate the process. Okay? And delta t is then some finite time you choose. Okay? That's possible. You can do this. You can use a fixed time step algorithm. Then you have to fix that time step. And once you fixed it, you can define the forward rate, and you can define the rate to stay. Now, what kind of problem could this algorithm have? Yeah?
That you have to choose a finite discretization time, whereas when you sample waiting time from this distribution?
Yeah, that's already good point. So you have to choose a delta t, and you have to choose this delta t small, right? Otherwise, you encounter what you said before the break, that you might have two events happening in delta t. So you want this delta t really to be small, that typically the delta t is smaller than tau, because tau was the waiting time to the next event. So you want it to be reasonably smaller than the typical waiting time between two events. Okay, so let's make it very, very small. Then you look at the probabilities, right? Then the one probability that will be the most prevalent is P naught. Because if you choose delta t to be much smaller than tau, then 1 minus nu times delta t will be basically 1. So that means you spend all your simulation time doing nothing. You spend all your simulation time with the particle staying put and not moving forward. Okay? If you make it too large, let's say you would choose the delta t something like larger than tau, then you have a problem with P naught because it becomes negative. That makes no sense either. So you're limited in your choices of your delta t, and this may depend on the model that you have. So it's becoming tricky to adjust the delta t appropriately. And the great idea of Gillespie is very simple. The idea is you sample the time. You don't choose a fixed delta t, but you actually do calculate the time to the next event. You introduce another stochastic variable, which is the time to the next event, and you sample the time to the next event from what we just calculated, namely this distribution function. Okay, then you know the time, you have calculated the time. There's no approximation whatsoever involved in that. And you don't spend time doing nothing because you determine the time at which something actually happens. Okay, and then you hop forward. That's it. That's the Gillespie algorithm. It sounds so simple, but it is so simple. The complications arise when you have a large network of stochastic processes is to do bookkeeping between the different stochastic trajectories that can happen and all the different processes that can happen. But the core element of the algorithm is always this, choosing the time to the next event. Now, how to choose the waiting time? We have done so already. So we know the distribution function. It's this. On a computer, and that's part of sheet 0, you have a random number generator. And hopefully it's a good random number generator giving you a really good representation of a uniform random number between 0 and 1. So that's what you have on a computer. A random number generator that puts out a random variable psi, and this random variable psi is uniform between 0 and 1. How would you use that knowledge now of a uniformly distributed random variable to get a random variable that is not uniformly distributed, but according to the law I just wrote down? Well, again, that's not difficult. So we want this, and we just say that we pick one random variable in the interval between 0 and 1. Then we have to pick the corresponding stochastic variable for the waiting time such that the two probabilities actually match. Okay? So the condition you have is the probability of choosing the time t is equivalent to the probability of choosing the random variable psi. Okay? Because it's the same event I want to sample. And then you have a map between the two because you now can translate one into the other. You just integrate both sides from 0 to time t, and then you need to integrate the waiting time distribution from 0 to t. And what you find is that this variable psi is 1 minus the exponential of minus t over tau. Now you turn things around because you want to know t. You're given psi. That means your time t is the log of 1 minus psi times the time scale tau that you have, with a minus sign. And now if psi is uniform in 0 and 1, of course 1 minus psi is also uniform in 0 and 1. So the point is you choose a random number uniform between 0 and 1, you take the log, multiply by tau, take the minus of that, and you get your waiting time. Okay? And that's what you need to implement on your computer. It's really just a few lines of code, and next week, Wednesday afternoon, there will be this Python crash course. What you will do in this crash course is also to learn how to precisely implement this problem, so you see how this works in detail. Okay? And please go there because using simulation in stochastic dynamics is really your experimental toolbox that you have in order to get some intuition about stochastic dynamics. And it's very easy, actually. All right, so hope you got this. Right, then this is the algorithm for the Poisson process. So as usual, in an algorithm, you set your initial condition. So you set your waiting time to 0, and you put your particle at position 0. Then you choose a random number, psi, uniformly between 0 and 1. You calculate the waiting time from that. You update your advanced time by t plus your stochastic time that you just calculated, and you update position from n to n plus 1. That's it. So once you do this in a Mathematica code, for example, this is what you get, and let's now discuss this a bit. So as you see here, this is a single trajectory. And the single trajectory, as you see, it has times where it steps forward. Right? This is the staircase that you see here going up. It always steps forward, and there's different intervals, like here a larger interval, here a smaller one, again a larger one. So different sized intervals, and the length distribution of these intervals is just the waiting time distribution, the exponential waiting time distribution that we calculated. Okay, and now from that simulation, you cannot just do a single stochastic trajectory, the staircase here. You can make many of those staircases and ask a similar question as before. What is the mean? What is the variance around the mean? So what's the dashed line? What's the width of the trajectories that you see close to the dashed line? That's the variance. And then you can even ask, given a certain position, let's say 60, if I sample at this position 60 many different trajectories, what is the density of lines that I find here cutting through these many lines? So to what probability distribution function does it converge? That's the probability that n of t is n at a given time that we talked about. Or you ask, you put yourself at this position here, and you want to know which one of those guys is first. And then you calculate the distribution of waiting time or first passage times to that point. Okay, so that's this. All right, so now let's do analytics again. And the way I'll do it is what's known as the master equation approach. And this master equation, it's called master equation because it's the basic foundational equation that you use in order to describe stochastic processes. That's why it's called master equation. It has the same kind of importance as, say, the Schrödinger equation in quantum physics. And there's actually analogies between the two sets of equations, as you will see later on in my lecture. So how do I approach calculating this? So again, this is this divide and conquer approach. I want this probability distribution function. And now I'm asking, what is this probability distribution function a little time increment dt later? So in pictures, you do have here time t with the different sides. So n plus 1, n minus 1. And here we have time t dt later. Again, position n plus 1, and n minus 1. Well, and now I'm asking, what is the probability of our Poisson stepper to be at this position n here at time t plus delta t? Okay. I can relate this to what happened just an increment of time before that. And the reason why I can relate the two is because I can dissect the probability of arriving there into mutually exclusive events that happen to bring you from a position at time t to this position at time t plus delta t. So you have to ask yourself, what are the possible options of arriving at position n? And there's only two, right? If you are here, right, you stay here. That's one way of arriving there. And the alternative, which is mutually exclusive, was a different type of event, is you start here and you hop forward. Okay? So what you then have is the probability of being here is the sum of the probability of starting out there and transitioning from here to there, plus the probability of being here and staying put at the same site. And that's the standard decomposition of a probability in a set of mutually exclusive events. So when I write what I just said in words, this is the probability of being at site n minus 1 at time t, and then hopping forward. So that's the conditional probability now, right? So this is not statistically independent, that's what I'm using. I'm using that this is the probability of being there at time t, and then given that you're there, what's the conditional probability of hopping to the next site? And this is this. Well, the alternative was I've been at site n at time t, and I remain there. So this is the conditional probability 1 minus nu dt of staying put. And we're done now, because that's, if I rearrange the terms, it's a differential equation. So let's write out this differential equation. d dt of p and n and t. Right, I'm just putting things on the left-hand side, such this becomes a differential operator. Then I have here nu times Pn minus 1t minus nu Pnt. That's our equation. That's the master equation. Okay, and you can again read it out, and then it's kind of intuitive that this equation has to be there. The change of probability at a site n in time is a gain and a loss term. I gain probability at site n if I've been at site n minus 1 before and hop forward. That's gain. I lose probability if I'm at site n, but I hop, so I leave the site. Okay? That's the loss. And when you have now a more complicated problem, and we'll do several of those as we go through the lecture, you'll find yourself soon enough that it's quite intuitive for you to write down these kind of differential equations. Okay, so it's a gain-loss equation. It's a balance equation for the probability. The probability changes in time because you have stochastic processes that change the probability either by increasing or decreasing probability. Of course, this equation has to fulfill a conservation law. Probability averaged over all sites has to remain 1. And that's, of course, encoded by this equation. You can check this for yourself. All right, now how do you solve that equation? First thing, what is it? What kind of equation is it? It's first order in time. It's a differential equation in time. It does not have what you usually have here on the right-hand side when you think about a Schrödinger equation or something like that. There is no differential operator in space. There's no Laplacian operator that gives you the kinetic energy or so for a probability distribution function. Instead, you have a difference equation here on the right. Right? This is n minus 1 position, n minus 1, and that's position n. So it's kind of a differential operator, but not quite. It's a difference between the values at different sites. Okay, now there are many methods of solving that. One method is just say, I'm not interested in P of n and t in its full glory. I only want to know the mean and the variance. Then you can use that equation and derive equations for the mean and for the variance. You can do this for your own. This is quite straightforward. Another one is to kind of do a continuum limit. This will actually not work for the Poisson equation, meaning you Taylor expand that term here, and then you get some differential operators. That's something we do later for the random walk. The method that I want to show you today is one that's called the method of generating functions. Now let me write it down and then discuss it with you. So I'm defining a function g of s and t, a bit similar to the characteristic function that we already had, because you now have an additional variable, which is s instead of n. And what I do here is I'm summing over the full state space from 0 to infinity, assuming now that my particle starts at 0. That's why I start the sum at 0. So I sum over all state space of all possible positions of my Poisson stepper. I take the probability and create a new function by making the probabilities being the Taylor coefficients of a power series. Okay. This you've seen. You may not recognize, but you have seen that. Any idea? In statistical mechanics, you change ensembles from canonical to grand canonical, and that's one of those transformations. Okay? And there, the fugacity is playing the role of S. Okay? And then things become easier when you have a grand canonical ensemble, because math is easier to do in the grand canonical ensemble versus the canonical ensemble. This also has a structure which is like other transformations. It's not a Fourier transformation, because for that you would need e to the I k something. But it's a transformation of that type. Okay? Instead of e to the I k something, you have s to the n. So it's very similar in structure to what you have as a Laplace transformation or Fourier transformation. It's just a switch of spaces from the space of the variables n to the space of the variables s. And later on, this is in about a few weeks, I'll show you that the switch from this equation to an equation for s is very similar of switching from a Schrödinger equation to a second quantized form. This would be the second quantized form of quantum physics. And the equation you get here is kind of the analog that you would find in Schrödinger's equation. But anyway, just take it as a piece of math that we use this transformation in order, and that's the game, the goal of the exercise, in order to get rid of this n minus 1. I want this on the right-hand side to be local. Now it's non-local. And as you know, Fourier transformations are used to transform a Laplacian into k squared, so making it from a non-local term to a local term. That's the idea. Okay? So let's do that, and let's calculate the equation that is obeyed by this generating function. Okay, so let's write that. Well, by definition, this is the sum from n to 0 to infinity, and I'm just here inserting the definition of that function, right? But now we know what this is, because that's just the master equation. So for this object, we insert the master equation. So you have sum of n equals 0 to infinity, nu times p n minus 1, t minus nu p n t s to the n. Okay, so how can we change the expression that we have there? We can shift variables. So we can make this n minus 1 to an n, tilde. Right, this would then shift the sum from n equal to 0, starting from n tilde equal to minus 1. But I can shift it back to 0, since the probability of being at minus 1 is 0. The particle just hops forward. There's no probability at side -1. So I can easily shift this to n tilde, and the only price I pay is that this needs to be s to the power n tilde plus 1. Here I don't do a thing, I just leave it as is, and then after shifting n to n tilde, I rename it back again to n. Okay, so let's do that. Then what you get is the sum from n equals 0 to infinity, and you do have nu times s to the n plus 1 minus s to the n, p of n and t. Right? So I can pull out the s to the n. Then I have in the bracket s minus 1, and I can pull this up front. So it's nu s minus 1, sum from n equals 0 to infinity, s to the n, p of n and t. And now you recognize the object is again the generating function, and the differential equation that I have in total is a prefactor times g of s and t. So the same kind of structure you would get in other instances when you do a Fourier transform or Laplace transform. You make it now local in your complementary variable, which is s and not n. And that differential equation here is again very easy to solve, given the initial condition, right? I need to do this. The initial condition that I have is that I want my particle to start where? At 0. Okay? So that's a Kronecker delta, n0, 0. Now I can use that to calculate g of s and 0. And the only term it will pick out from the whole sum is the one with n not equal to 0, so this object will just be 1. Okay, so this is 1. And that means now that our distribution function, g of s and t, the generating function, is e to the nu times t times s minus 1. So it's an exponential, as we have seen, a minute ago for the survival time. That's our generating function. We're not done yet because we need to go back and find the back transform. So for that, you would, if there would not be a trick that I'm going to show you for this particular case, you would need to be inverting this relation. And I don't know whether you've discussed this in your statistical physics course. There's a formal way of inverting the transformation from canonical to grand canonical ensemble. It's basically by contour integrals in complex space. Okay, so you can do this. Here, it's actually a bit easier because in the end, what we want is we want it in the form of a Taylor expansion, because the Taylor coefficients are the probabilities. So let's just Taylor expand this. So let's do that. I'll pull out the prefactor e to the minus nu t, and then I Taylor expand e to the nu ts in its known Taylor series. So you have from n equal to 0 to infinity, and that's the standard form of a Taylor series of an exponential s to the n. And now you're done because, right, this here needs to be our probability distribution function because that's how we defined it. Okay, so in total, p of n and t read off from this calculation is e to the minus nu t to the power n divided by n factorial. That's it. And now I think you finally see why this is called a Poisson stepper, because that's a Poisson distribution. One of the standard distributions you discuss typically when you discuss statistical, stochastic probability theory. All right, what can we read off from that? We can read off the mean and the variance. Okay, what you find is that the mean of n and t, any guess? Nu t, that's pretty obvious, because you hop forward with a constant rate, so the rate is your speed. This is a deterministic ballistic process. What's the variance? Yeah, you know this, right? You have not done this in your head that this is also nu t, but it is. So the variance of n and t is also nu t. And that's quite a strong statement, because it says if I now would compare with experimental data and I measure the mean of my kinesin motor and I also measure the variance of the kinesin motor, I should get the same number. It's a very clear-cut prediction. Okay? And what you find, it doesn't fit. It doesn't fit. It's not quite, the ratio of variance to mean is not quite 1. It's something else. And I forgot whether it's a half or 2, but I'll figure this out for you next time. And that tells you that, our approximation is not so bad. It's pretty close to what the actual process does, but that there's an underneath secondary process with a second time scale, not just the time scale of hopping, another time scale that comes in. And when you do the analysis, and that's something in the problem sets, if you take a two-state model where you first need to activate before you jump, then you get a reasonable description of the experimental data. Okay? And that's often how things work if you analyze a complex biological problem. You look at the problem, you make it as simple as possible, but hopefully not too simple. Do the calculation, compare with the data, and then see whether you're right or wrong. And if you're wrong, you improve your model. Okay? All right. Now, what's the time? Are there questions? Yeah? Yeah. Because they are gain and loss equations. So on the right-hand side, you will always have, so this is the change of probability. And on the right-hand side, you have a dissection of your stochastic process into alternatives. And these alternatives each have a certain probability times the transition rates to go from these alternatives to the state you're looking at. And that's why on the right-hand side, you'll always have, of course, very complicated terms, but they're still all linear. So in general, the equations will always look like this. You have d dt, and then you have a probability vector as a function of time, okay? Instead of just something like this. And this vector then is related by a matrix to this object here. So that's the general structure of a master equation. And that tells you something, because now, and we'll do this also later in the lecture, you can study the properties of Markov processes or stochastic processes by studying the features of these matrices. And those matrices, in distinction to a quantum system, they are non-Hermitian. So the eigenvectors are not real necessarily. The eigenvectors can be complex. And there's not just right eigenvectors, there's right and left eigenvectors, etc. In the course I gave, I think that was a year ago, we discussed this at length because there I connected the properties of this matrix to properties that are studied in topological phase transitions in quantum physics. And there people study the properties of eigenvalues and eigenvectors and relate them to topological protection of certain quantum states. And the same question you can ask here, is there some kind of topological protection of stochastic stationary states of the system? Yeah.
You mentioned in the beginning of the lecture there's some analogy to the Schrödinger equation. Is this basically what you want to say, but we have to replace p by psi?
So exactly. So in the Schrödinger equation, psi is not a probability. It has a very different interpretation. But the mathematical structure, once you are in a picture of eigenstates, is the same as this. And the difference is two things. P is a probability here. It's not in quantum physics. And W is not a Hermitian matrix. It's a non-Hermitian matrix. That's the difference.
And you lack the I, right?
You lack the I, but that's a minor detail, let's say. The key difference, the I is also important. And it's more important that the interpretation of the object is very distinct.
So it's not the analogy there, because it's not.
It's mathematically similar in structure. And so the point is, often people say quantum physics is quantization. That's not true. Because there is quantized states here as well. They just have a different reason because these are eigenstates of a matrix. And there's transition between these eigenstates. So that's not the characteristic of a quantum system. The characteristic of a quantum system is the entanglement that you have in the quantum states. And that's something you don't have here. And that has to do with the interpretation of the objects and the structure and the I, etc. Other questions?
Is there also something like an interaction picture here?
Yeah, you can construct perturbation theory. That's what this picture is often used to. And you can also construct perturbation theory for these classes of system. And we'll come to all of that. So we'll analyze solutions of stochastic equations. We will see how we can approximate them, and so on and so forth. Yeah. But really, I mean, this whole thing is about differential equations, right? And at the level of mathematics, all you do is you find different representations of differential equations. And one set of representation is in terms of ladder operators, and the other representation is in terms of differential operators. The ladder operators are basically that here's a ladder operator that makes n to n minus 1, so you have a destruction operator here in front. Okay? And here you have a number operator in front because nothing really changes. So that's the representation in terms of lowering and raising operators, while the representation here in terms of the generating function, that's the analog of the representation in the Schrödinger equation picture. Okay, and these mathematical analogies are very, very strong because you can do a path integral formulation of stochastic systems, which was way before the path integral formulation of the corresponding quantum systems. And all these formulations in terms of path integrals are super useful in stochastic processes, much more, I would say, in stochastic processes than actually in quantum systems. All right. I think I cannot really start a new thing, but I want you to get started and think about it. So the next step that we will do is population dynamics. And with population dynamics, you can mean a lot of things. You can think of population dynamics of real people. You can think of population of viruses. We had a virus, spreading among us for some time, still spreading. And you can ask yourself, can I formulate a mathematical theory for these types of populations, viruses, bacteria, opinions on the web, etc. And that's the field of population dynamics. And usually what it deals with is different types of species. I call them A, B, C. So you may think of one type of bacteria, another one, and the third one, and say one bacteria produces a poison that kills the other one grows faster than the first one, so things like that. So different types of individuals, let's call them species. Now let's look at the most simple process, which is called the simple Des process. That means we consider just a single species, let's call it A, and I say it's dying with a rate lambda. You can also call this a decay of nuclei, right? Radioactive decay, that's the same thing. Certain number of radioactive nuclei and their decay. So now let's, and maybe we do this together, to write down the master equation. And lambda, okay, I have to say this, lambda is the per capita death rate, meaning the likelihood or the rate at which a single individual dies. Okay? So what's the master equation? What should I write down? Give it a try. The picture that helps is this. Right? You have time t, you have time t plus delta t, you arrive at n. How can you arrive at n? You die or you stay alive, right? That's the two options. So what's the gain? How do you gain a population of size n? Try it. Yeah? Go ahead. Say?
The amount of population plus one dying.
Yeah, exactly. So you start out with a population of one individual more. So that's our starting point. And then you die. There's a conditional probability of dying now. What is that? So lambda is per capita, right? It's gain, right? So it's plus lambda. So lambda is right. But times what? Times n plus 1, because each of the n plus 1 individuals has the same chance of dying. Okay. How do I lose? Not harder than that, right? So you start from nt and you die. So minus lambda times n. Yeah. Okay, so that's the master equation. And there's a tutorial, which is here in my lecture notes, that says just repeat the same steps that I did for the Poisson process and calculate the corresponding probability distribution. And I think you really should do this because this is step by step following what I did, and you can just check whether you got a good understanding of how you actually solve the master equation by the method of generating functions. All right? Questions? Anybody? All right, so let's stop here and summarize for a second. So the most important thing from today you should take with is that there's this Gillespie algorithm, because that's the heart piece of simulating stochastic dynamics. And the second hard piece of stochastic dynamics is master equations. And I showed you how you set them up in simple terms, and then there are various ways of solving those master equations. And with all theories, right, the equation to write down is often much, much easier to actually solve it. So a lot of the part of the lecture will deal with how to actually solve master equations. Not exactly, but approximately, because that's the real art of approximate solution of complicated problems. Thanks for your attention.